Oscillators, a basic training by me, Nick Amy. However, quartz is not the only resonator type. There's quite a few different options out on the industry at the moment. So let's run through them and have a look at the different parameters that they cover. If you just want a very basic oscillator, you need something that switches on and off at a reasonably regular state, but you're not overly interested in the accuracy of the timing of that. You could start with a very basic LC circuit. A lot of us came across these at school. We used a 555 timer and we put a capacitor and a resistor network on the output of that. And what happens there is the capacitor is charged up and then it discharges through a resistor, and in discharging through the resistor controls the discharge time, and so we have a time constant developed over that. This type of circuit is not very accurate. It's just stable to maybe 10% if you're lucky. It'll change frequency depending on the humidity, the temperature, the air pressure. Pretty much any parameter change will cause a frequency change on these things. They're very, very cheap, obviously, so we're talking fractions of a cent here. And it's hard to get above about 500 kilohertz in these circuits. So there's definitely scope to do better than that, but there are times when that's the right option for you. If you want to go up in the frequency control chain a little bit, you might move to a ceramic resonator. Ceramic resonators are products that will give you a stability that's a little bit better than an LC circuit, but not much better. So again, best used in a situation where you will need to execute some code, so you need some clock signal, but it doesn't really matter to you if that clock is changing a little bit. Perhaps there's no communication with the outside world, it's running in isolation, you just need it to run sequentially, keep the bus speed running. So these things might cost in the region of a few cents, and you can now run in the megahertz region, so maybe 3 megs to 70 megs, that kind of area. They are in fact a piezoelectric material called lead zirconium tantalate, PZT. So there is a coupling between its shape and its resonant frequency. However, if you want something where time is actually starting to become important to you, the timing of events and synchronizing events between one area and another, then you're going to be looking at a commodity quartz oscillator. So commodity quartz oscillators are the types of things that we might store in large volumes and sell in reels of thousands. Stability for these products for a TCXO can be less than a ppm, or for a standard crystal might be in the range of 100 ppm. The frequency ranges for these are 1 megahertz up to 800 megahertz, and there is of course the 32.768 kilohertz devices which are used for watch crystals and real-time clock circuits. So the resonating principle that's happening here is the piezoelectric effect of quartz crystals. That means that we shape the quartz to have a physical shape with a resonant frequency, and the coupling between electrical and mechanical principles as described in the piezoelectric effect means that there is an electrical resonant frequency. So as we change the shape of the crystal, so we change the resonant frequency both electrically and mechanically. That's not the only form of resonator. These days there's also a new resonator on the market known as a MEMS oscillator. MEMS oscillators have stabilities and frequency ranges which are very comparable to commodity quartz oscillators, and that would be because when they first came into the market they were looking to be a parallel product to the quartz oscillators, so that was their target, to hit the similar spec. The actual fundamental principle that's going on inside is it's a piece of silicon that's been shaped and formed to have a resonant frequency. So there is in fact a piezoelectric coupling between silicon here. It's very, very small, so it's produced in the fabrication process, very similar to normal CMOS fabrication. Maybe one of the main differences between a MEMS oscillator and a quartz oscillator is that the MEMS resonator system will have one frequency that it resonates at, and then there'll be a PLL circuit that's shifting that into different frequencies, whereas with quartz you tend to grind and lap and polish the quartz to make a specific frequency from that. So the main reason why the two might differ, it would be on the phase noise. On a phase noise plot for a MEMS, you might see a bit of a hump caused by the PLL circuit, although I have to say they've got very good over the last few years, so they're not such a problem as such anymore in the applications they're used for. However, there are times when that's just not good enough, and there we would move up to the next level, which would be a high stability quartz oscillator. So that could be an OCXO, and an OCXO in today's world is available down to frequencies in the range of 0.2 parts per billion or 200 parts per trillion, and that would be the type of frequency deviation you might see caused by temperature from these products. Costs are going to be a lot higher. Frequencies are going to be more limited because it's much more complicated to design these, so I can't do all the plethora of different frequencies needed, but I can give very stable stuff in sort of 10 megs, 100 megs, 80 megs, very fixed frequencies like that. Internally, what's happening is it's the same as a commodity quartz crystal. It's a piezoelectric coupling of the resonant shape of the quartz, but we will go into a little bit more detail on the next few slides about how we achieve the better spec from these parts. If you want better than that, the next step up would be a rubidium oscillator. Here what's happening is a rubidium physics package is coupled to an OCXO, and the combination of the two will correct the aging that's happening in the OCXO. So the stability is similar to what you get in an OCXO, and then where the improvement is in the very long term. So over the year, you'll get a lot less frequency drift. The cost is a lot higher. The internal frequency of these things is 6.834 gigahertz, but then your external frequency that the customer is receiving is normally the OCXO frequency of 10 megahertz or something like that. The actual resonating principle that's happening for rubidium is that we are going to excite the rubidium 87 gas. We are going to excite it with a microwave frequency, and that's going to create a hyperfine transition as the shells of the electron shift from one state to another. They give off photons as they do that, and if we get the microwave frequency exactly at that 6.83 gigs, then it gives off the maximum number of photons, and so by looking for the maximum number of photons, we know that we've got the right microwave frequency, and that's our feedback loop. That's our resonating principle for these ones. If you want better than that, you're going to shift into a cesium clock. Cesium clocks have even better aging performance than rubidiums, so now we're looking at figures like 1 times 10 to the minus 12. These things are going to cost between $50 and $100,000, so much more expensive. The concept that's going on inside is similar to the rubidium in as much as you've got a microwave transition, but instead of rubidium gas, it's now cesium 133 atoms, and they are going to go through their own hyperfine transition, but instead we're going to need 9.192 gigahertz because that's the microwave energy frequency necessary to create the hyperfine transition. One thing that's worth noting with a cesium clock is that the current SI unit of time is the second, and it is defined by the decay of a cesium atom. So a cesium clock is the definition of a second, which raises an interesting question to say, how could you possibly be better than what is the definition of a second? But there are products that are better, and the next in the range would be a hydrogen maser. A hydrogen maser is a product with an aging even more improved on the cesium clock. So here it will be 3 to the minus 16 in 24 hours, something in that area. Although the cost is going to be a lot higher, so $250,000 to $500,000 for one of these. Internally, it's a similar concept to a cesium and a rubidium in as much as the hydrogen atoms are doing a hyperfine transition. Because it's hydrogen, it's a different frequency again, so we need 1.42 gigahertz for this one. But again, the output frequency would be 10 megahertz as derived from a quartz crystal, and the physics package is just correcting the aging of the quartz crystal. And finally for this slide, the optical clocks. Optical clocks are clocks where the internal frequency is running at tetrahertz, so that's up close to the visible light frequencies, hence the name optical clocks. The aging on these things is equivalent to sort of 1 second in 15 billion years. I want to say that they are in development only. I'm giving this talk at the end of 2024, and beginning of this year I was seeing things being discussed about how they could condense it down from a science experiment to being something that could be sold. And then at the end of this year, I saw 2 or 3 companies that were offering these things as 5U rack-mounted objects. So products that could be sold, although they were telling me they could only produce 2 or 3 of them in a year. So I would say watch this space. These products are coming into the market quite quickly at the moment. Okay, I have a line across there in the middle of that slide. That's because the products above that line are PCB mountable devices. So they're things that you would buy as a electronic component, solder them onto your PCB and build a clock out of it. Whereas the units below the line are standalone units. That means they are rack mountable items that you would buy, plug into your rack, connect via a cable to something else, and they would give you a frequency output on a BNC connector or something like that. Okay, so there's a summary of the different resonator types that are available in the market today. So thanks very much. That was a brief summary of general state of oscillators across the industry, and hope for some insights into how they're manufactured and what to look out for them. There's some further reading here if you're interested, and we'll be doing a lot more of these in the future, so do check back for more.